Okay, my friends, I am in high gear today. It's a 2 cup of coffee day. And I'm rocking. I'm going to tell you this. I have a lot of fun in this realm because I think I fully understand what is going on with fission and fusion. It's very confusing to people. They say it's the most confusing thing there is, and it involves neutrinos. And I go with the top people, who is Fermilab, CERN, Brookhaven. They're showing these particles, the matter and antimatter, Dirac neutrinos. I agree with that 100% with Don Lincoln about the neutrinos. And I also agree with him that these are the two smallest particles that exist. One of them is like a bowling ball, and the other one is just a burner. All right. Now, so far we have seen what the tiniest particles exist are, and they really these two make up the neutrino. The two black and white, the black and the white. Okay. Now they also say, what do we have here? Okay, that these are nothing more than light particles, and empty space isn't empty. This is all Fermilab again. So they agree space is filled with these particles. And what do we have here? All right, well, here we have fission and fusion. I'm going to explain to you, and I'm going to actually show you what fission and fusion is. So let's go into that right now. Okay, my friends, I think we got to get a little deeper into fission and fusion and all those things before we can go into the black hole in space, because it's important for you to understand the particle nature that we're dealing with. And then we'll go to Hubble's black hole in space and how this formed and why these things are entangling and forming all these loopy swirls and all these things. Now, they're showing only graphics. The stuff I show, as you have seen, are not graphics, they are actual experiments. So, before we can get into looking into how Hubble deals with space, let me show you how I deal with particles and space as well. Okay, my friends, if you've been breathing oxygen, you've been hearing everybody talking about fusion. We got to do something to get some energy for free. And fusion is supposedly free energy if you can do it correctly and efficiently. Well, it has not happened, and they are not going to be able to do it correctly and efficiently until they scale it down, which is what these people are trying to do, only they're really not scaling it down. I can scale this down to something you can carry around in your hand and use that. Let me show you what they're doing, and I will show you what I am doing. I can't create this myself. I need some funding, or I need some people in the energy department to take hold of this and do it. It's a very, very simple process once it's understood. Okay, my friends, I think we have hit the point where it's time to really cash in on fusion. Now, they, in the physics world, think you have to take big particles, smash them together, and then end up with one smaller particle, and then the debris is energy. And that is true. It's just like when you burn something. You're not smashing them together, you're burning it, but the debris is energy, it's heat. That's what they're looking for, is heat. We can do things differently. We can go right for the electrons. We can go right to the electrons. Now, that's what this new company is trying to do. However, I think we can do it in, is about this big to do this. We could put this in here and have hundreds of these, because the actual interaction spot is like that big. So you could have tons of those in a small little device like this. Carry it around and then have your little outlets in there. You could plug anything you want into it. And it's got no grid, nothing. Now, how would we do this? That's a laser into a Venturi. Here it is right here. It's a laser into a Venturi. Now, he's going to be talking about pulsation. They're going to be talking about electron absorption. They're going to be talking about field effects. All of that is right here. This is the particles, these two particles they can see at Fermilab and CERN and Brookhaven and all that. But they don't know where they come from, because they're smashing big things together and they're just getting debris. We use the light. Now, if you take a particle or a proton, that's not light. Light is way, way smaller than a proton, because a proton is not even anything like this. A proton is parts of light, pieces of light. It's all it is. It's condensed light. All right, when you take the particles of light, which are these right here, that's all it is. This is light. These are photons. And you crush them down together, at a certain point, there's a quantity of them that becomes stable. And that is what they consider to be a proton. I say it's 1823 of these particles right here, which is the black one and the white one tied together, or green or blue or whatever it is. They are the Dirac neutrinos. And they create the photons. We actually separated the photons, precisely what Fermilab and CERN wants to do, but they're doing it inside of huge, huge, huge devices. Very, very expensive, very complicated. We're going to be able to do this in a handheld device, just carrying around a little tiny laser. I mean, a whole device is about that long. I'm not kidding you. That's all it is. And at this point right here, we put our harvester in. So we don't have to collect from the outside of an explosion the heat. We're sucking these electrons, and at this point, that's all they are, is electrons. This is what would be induced into the fields that I'm going to show you in a second. They're doing a helion. Okay, stick with me on this. Very simple. This is what they consider to be a hydrogen nucleus. That means that's the center of the hydrogen atom. And then there's supposed to be one little tiny electron, which is 1823 times smaller, floating around here with an opposite charge. Big, huge positive with exactly the same charge as the negative, but opposite. And for some reason, they don't attract each other, which is nonsense. It never did work. The standard model is very wrong. They're dipoles. This ends up being this. Okay, all these particles are electrons. Every one of them is one of these. So this particle right here is a magnet. All right, it has a dark side and it has a white side, just like all bar magnets have. They have a positive and a negative. When you add enough of these together, and two of these together, let me show you what makes light. Don't forget, this is the Dirac neutrino, a white and a black. This is the Dirac neutrino, the white and the black. This is a Dirac neutrino. This is a Dirac neutrino. Well, what's going on? They can actually separate, and we did separate them down here. I will show you that in a second. But normally they are attached together exactly like a bar magnet, as I showed you. Now, when you put two of these together, they become light. And when they are just these together, two of them by themselves, they are an electron. We never knew the black side was attached. It was all we ever saw was the glowy side that pushed back at us to give us energy. We could see it. We can't see that. You can't see that. It's dark. That's why it's dark matter. And it's an attractor. It sucks these white ones right back into it. And I got to think now that the black attracts its own self, because that's what they call the Majorna electron, neutrino. Whoops. Hold on a second. That's what they show as a twisted photon. But here's what they're showing for the Dirac and the Majorna. The Majorna has pretty much the same energy on both sides of its equation. This one is totally one side and totally the other side. Black and white, positive and negative. Okay, my friends, this is where it gets really interesting. Now, types of nuclear radiation. There are different types. Now, this is Fermilab. I follow Fermilab pretty close. But this is the difference between fission and fusion reactions. Well, what is the difference? Both fission and fusion are nuclear reactions. They happen within inside the nucleus. And don't forget, this is my nucleus. It's not one of these. It's a whole batch of these. Now, both these fission and fusion happen within inside that nucleus. And they produce energy. The processes are very different. There's another process that produces energy, and that's burning something. So let's take all three: fission, fusion, and burning. All right, now, fission is splitting of a heavy, unstable nucleus into two lighter nuclei. All right. Well, what is burning? Burning takes something that's combustible and burns it, and all stuff goes away, heat and energy and everything, and it reduces it down to different matter than it started with. All right. So here we have a splitting of an unstable nucleus. So we're talking about unstable matter. Nucleus is just because it's subatomic. And it breaks it into lighter nuclei, and fusion is the process where it comes back together. The two light nuclei combine back together, releasing vast amounts of energy. Now, that's because they are in this nucleus. When you burn something, you're not inside the nucleus, you're outside the nucleus, dealing with the bonding of different matter, so that it basically breaks it down into its components, and they give up some of their energy, and that's what the heat is that energy. However, once you're down in the nucleus, you're not just throwing off a chunk of this and a chunk of that. You're throwing off all of these as a particle at a time, and that's, each one of these is basically what they would always consider an electron. So you're throwing off electricity. When you fuse those two, they take two big ones, all right, and they smash them so hard together, or they heat them up so hot that they just fall apart, and when they come back together, they give off a bunch of energy that would have been part of its structure, and it goes flying everywhere as heat. That is what they're harvesting in fission. Well, they have to break it apart first of all. You always have to have fission before you can have fusion. You can't have fusion without fission. You have to break apart the particles to make them come back together. We did it with light. We did the same thing they're doing, only we didn't use nucleuses. We used photons, and we did it with light. All right, so don't forget, here's what they did at CERN and Fermilab and Brookhaven, all of them. They take huge protons and they smash them together, and then they get all this debris flying out. They see the black particles, they see the white or blue or green, or I'll show you what they do see, because it's exactly what is expected because of my theory. Now, what we did, instead of hitting them together, all they're doing was forcing these fields to concuss so hard that they exploded. It's called the Kashmir effect. We caused the fields to collide together. This is almost like a funnel. All right, it goes like this. And all the particles have to come together. Well, guess what? The black ones can't get through. We made it so tight that the black ones can't get through. The white ones can squirt through. They're really fluffy, and they can just go right through. So these keep bashing, and they keep squirting the white ones. It's just like a jackhammer. It's a pulsed laser. So here, instead of this hitting head on and just trying to find out where the debris ends up, we did this right through the venturi. And guess what that means? That means that the black is the jackhammer. Bam, 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 bam. The white is along with it, and the white has to get the hell out of the way, and it pushes it through, and it splatters it as literally half of the Dirac neutrino onto our substrate, and we should be able to harvest enormous quantities of energy there. Enormous, and right through the substrate, nothing else involved. You should be able to carry this around as a device, just like that. These things are so tiny that you could have, I don't know how much energy you could come out of here. You should certainly be able to power a house or a car or something with this, using this. If this is correct, what they say about the energy values of muons and electron neutrinos, we're off the charts here. You're into at least billions and possibly trillions of electron volts versus 100,000 or so. That's a big increase. All right, as you saw, these are the Dirac neutrinos. But in the center, as in the protons, this is what the Majorna part is the black center. Now, in outer space, they just actually did it. They did it, the Russians did it in outer space. They created a black hole. They didn't know they did it. And this is where the crust comes around. This is nothing more than what electrons is coating a black hole. And that's because it was done in zero gravity in space in a vacuum chamber. Now, we accelerated the light right here from a pulsed red laser. As I told you, it starts to stack up on itself, creating different styles of neutrinos. All right, they call them flavors. They say it starts out as vanilla ice cream, and then it turns into pistachio, and then it turns into chocolate, and then it turns into tutti frutti. They claim there's different flavors, and there is. As it stacks up, it displays differently, and that I can also show you. You see right here? This is as it's coming in. You see, that's a neutrino. This is a photon, but there's also neutrinos. You see these ones here? These ones go this way. There's a different flavor on that one. The photons are different than the rest of them. And then you get these little glowies on one side and the other side, and they're all kinds of crazy energy values. But primarily, this is a photon. Light is basically that particle. It separates over there in the Venturi. You just never see these particles. They're all up in here, too. You just can't see them because they're not in line with the concussor. That's our accelerator. If you don't have that in direct line, you're going to get some little bits of things. You see how, like these up here, they're up there, but you can't, back here, you would never see them. You see that? There's nothing there, it's all zero. But down here, yes, we're starting to see ours starting to glow. Why are they glowing? Because they're directly in line with the accelerator Venturi right there. The rest of them are not. So it's only that one little beam. But that's what the laser does. It funnels them right into a beam, right through there, and we're going to harvest on the other side. I don't see why we can't get that free energy. Now, the green and the blue is actually the same particle. It's the exact same particle, only much faster and more powerful. But it also does the neutrinos, the same thing. They stack up. As they stack up and get ready to concuss, they display different intensities of energy. That's basically all it is different intensities of energy. When I say we can squirt them onto a substrate, I'm not kidding you. That's that white, pure white electron neutrino shower. And once it concusses with the rest of the universe, it creates these Higgs fields. And we can create this all day long. Never have to stop. Just let it keep going. All right, so that's what we're just looking at is right there. This here is right there. Okay, now, at that place, we put our harvester in right here and run it down through our equipment and let it come back to its black side. Right here, you see it? The laser shoots it out. It stacks up here. The black ones just leave. The white ones, the reason I put these different colors here, we would have to use some really good CMOS technology. They call them Perscovites, or now I believe they call it, which is nothing more than transition metals and other different metals that will absorb these electrons as electrons and then funnel them down through here and then through batteries and so forth, and then our load and let it get back to its black side, and everybody's happy. But we can use that energy in the meantime. That's all that is a battery. A battery sends electrons through when you want to use them. It just sits there holding them when you don't. And when you want to use them, you take them. But you have to start with a whole batch of electrons. That's what we got right there. Now, everybody says, oh, Roger, you should just go do this yourself. Well, no. For 7 years or more, 8 years probably, we've been doing this, trying to present it to the people that have the money to do this. So we don't have the money to do this. We only spent $500 tops to do everything we did. But we did better than they did, and they're just upset because we did better, and they don't want to talk. So that's the problem, is that it's the intransigence in the people that are spending trillions of our dollars and really getting absolutely nowhere. And the complexity is just staggering. It's never anything that's going to help the average person. And it's never going to get us off the energy grid. It's just a mistake and a waste of time because they don't understand the particles they're dealing with after all of these years. And it's because of peer review and forced compliance with the standard model. It does not work. All right, this is the model that does work. And basically, that is the model. It's as simple as that. Now, it does change a lot of stuff. It completely changes the periodic chart. The periodic chart has to completely be changed, which is not a problem. I've already figured that out. It's very simple, actually. Now, the other thing is the actual look of the proton and the look of molecules has to change to incorporate these zones of energy. And how can I say that? Because I'll show you what CERN and Fermilab found. They found those zones of energy, don't realize it. Okay, I'm going to show you the difference between our Higgs fields and CERN's Higgs fields, Fermilab's Higgs fields. Ours are what's called coherent light. So we're getting red. We're getting just an exact certain frequency of energy that's concussing, that's creating the red. When you have all different frequencies of energy concussing, you get all different frequencies. And they're using protons, so they have all those different frequencies. We're using photons. We have only one frequency. So that's why we have only one color. Now, you see in theirs, so don't forget, this is ours. Now, this is one that got squished together. That turned blue. That's very unusual. But normally they stay pretty much the same color as what the frequency that's hitting it. In this case, it was a red pulsed laser. Now, the green does exactly the same thing, as I probably showed you. All right, it's exactly the same thing. And here's the difference between the two. Here's green. Very powerful. Look at that. They don't concuss until they're way out there. And these are the particles, the same particles. All right, now, but they're much more energetic. Now, that's the green. Now, green and red together, we can see the difference right here. You see it? The red has almost nothing. The green comes through, pushes the red right out of the way, and keeps going, and concusses way out here. And here's the green particles mixed in with the red. They have almost no energy at this point whatsoever, and the green is very energetic still, and it reconcusses out here. So, we have seen my Higgs fields, and now let's understand CERN's. Why do they have all these different colors, and why do they have these little straight lines and all these little round things? We're showing the same Higgs fields. Okay, let's just finish it up here. These are our Higgs fields. This is CERN's, or Fermilab. You see all these little, that's exactly what we have here. But they also have some really high, and we do too. These are high energy particles. See, coming way, before they show up, they're way out here. These show up instantaneously. Same thing with theirs. The reds are just the weakest ones. Because they are, here's the deal. In their protons, the red ones are way on the outside. Then they get green and blue go right real tight because they're really held in there. When you knock those off, they just, they go like a rocket ship. These sort of bounce off easy, and they just form those fields. That's what the difference is between protons and photons. We use photons, so we're just using these particles of light here, right there. Right there, that's all we're using as a photon. So we can't get these crazy colors. They can get the crazy colors here, you see. But they're the same particle. They're doing the same things our particles are doing. The greens and the blue go like crazy. The reds are that fluffy Higgs fields like you see here. And the white is even sizzler. And we see all of those in our experiment, all of them. And the white one here, you can see these are very, very simple. Where's a white sizzler? Well, let me show you in the Higgs fields. This is really cool, the sizzlers. Alright, these are the white sizzlers. You see them coming up? Zip, zip, zip. That's exactly what they're showing from the other ones. And then they turn into the reds right away. The blues and the greens, they just take off. They really rocket ship out of it. Alright, this is nothing more than a sideways version of a head-on. They're seeing all the reds and all that stuff, and then the real shot. We're seeing it come through, and we see a red, and then we see the green real powerful, and the blue would be way out here. We didn't run the blue through, but the blue is just very powerful. You see it? It's so powerful you don't even see it as a particle. You see it as just a bzzz, and then start to break apart out there and show that it is two particles and not just one. And they spin, just completely spin like this. Bzzz. And all of them do exactly the same thing. They all do the same thing, only the concussion values are completely different, all three of them. And the blue is a real, in the crystal that produces that blue light, it has to be holding those electrons really tight. And then the red is just a loose held electron. It's just loosely held. Because they come out of here and they don't have anywhere near the energy the other ones do. So I think I made my case pretty good. And I think we should do what we can. At least somebody should look into this. So hopefully somebody will. I mean, it hasn't happened so far, but I'm willing to work with just about anybody. I just need somebody to see this stuff and understand the nature of everything is dipoles. Even the nature of planets and space and everything, they're all dipoles. It just was missed. That's all. Okay, it's obvious we're going to need a third part at least. Now, this is NASA, and they're saying that they found this black hole and a planet or whatever exploded, and all of its parts got sucked into that black hole and formed this disk. Where do you see what they show here?
Swirling around a black hole. The swirling gas was once a star. Usually...
All right, then we get into this. Now, I am going to get into this because I think I understand this quite well, and then it falls into this. Why does space smell like burnt steak? What's going on with that? We're going to have a whole new realm of things to talk about space in the next video. And it'll start with how these black holes form, as I showed you how they form in space right here. Right there. That's how they form. Now, and I can show you this actually forming, all these particles swirling around. It's exactly what they showed in NASA, because this was done in a vacuum chamber in zero gravity. That's why they never saw it before, because gravity pulls all the particles in. If this was the Earth, they'd all be laying on top of the Earth, so you'd never see the hole. So inside the Earth, there's got to be more dark matter at least, and maybe a black hole.